I am Shridevi Masuti, currently Assistant Professor in the Mathematics Department of IIT Dharwad. I will give two lectures on complex numbers. In these lectures, we will discuss a few problems on complex numbers. Let us begin with the first lecture.
Let us consider the following problem. Let Zk be a complex number whose real part is cos 2k pi by 10 and whose imaginary part is sin 2k pi by 10, where k is in the range 1, 2 and so on up to 9. Then the question asks which of the options given below are true. This is a multiple choice question, so it may be possible that more than one options are true. Let us see what are the given options are. Option A is for every complex number Zk, there is a complex number Zj so that the product of Zk and Zj is equal to 1. Option B is about the absolute values of the complex numbers, which is the product of the absolute value of 1 minus z1, the absolute value of 1 minus z2, and so on up to the absolute value of 1 minus z9 divided by 10 is equal to 1. Option C is that summation of k goes from 1 to 9 cos 2k pi by 10 is equal to 1. Option D is that summation of sin 2k pi by 10 where k goes from 1 to 9 is equal to 0. Let us see each options one by one and check whether they are true or not. Let us consider the option A first. We are given that Zk is equal to cos 2k pi by 10 plus I sin 2k pi by 10, where k is in the range 1, 2 and so on up to 9. Recall that this complex number is equal to e to the power I 2k pi by 10. These complex numbers are very special. They are known as the 10th roots of unity. What do you mean by this one? This means that the 10th power of Zk is equal to 1 for all k belonging to 1, 2 and so on up to 9. There are many properties of these roots of unity which are well known. We will recall these properties as and when required. First of all, observe that for every integers k and j which may not be in the given range, Zk times Zj is equal to Zk plus j. This is not difficult to prove. In fact, is a consequence of complex multiplication and the laws of indices. But let us see a quick proof of this. So we have Zk times Zj is equal to, recall that Zk is equal to e to the power 2k pi by 10 that j is equal to e to the power I 2j pi by 10. By the laws of indices, this is equal to e to the power I 2k plus j pi by 10. This is equal to zk plus j by definition. In particular, if we take j equal to 10 minus k, then zk times zj is equal to zk times z 10 minus k is equal to z10. But what is z10? So if we put k equal to 10 in the definition of zk, we get that the real part of z10 is equal to cos 2 pi, which is equal to 1, whereas its imaginary part is sin 2 pi, which is equal to 0. And thus z10 is equal to 1. Also, observe that since k is in the range 1, 2 and so on up to 9, j equals to 10 minus k is also in the range 1, 2 and so on up to 9. Thus, for every complex number zk, there exists a complex number zj such that zk times zj is equal to 1. Hence, we see that the option A given to us is true. So, let us mark this option. Let us consider the option B now, which is on the absolute values of the complex numbers 1 minus z1, 1 minus z2 and so on up to 1 minus z9. Recall that for a complex number, z is equal to x plus iy, the modulus or the absolute value of z denoted as mod z is by definition positive square root of the real number x square plus y square. It is well known that if z1 and z2 are two complex numbers, then the absolute value of the z1 z2 is equal to the product of the absolute value of z1 times absolute value of z2. Inductively, one can show that the absolute value of the product of the complex numbers z1, z2, zm is equal to the product of the absolute values of Z1, Z2 and so on up to Zm. Using this for our problem, we get that the product of the absolute values of the complex numbers 1 minus Z1, 1 minus Z2 and so on up to 1 minus Z9 is equal to the absolute value of the complex number 1 minus Z1 times 1 minus Z2 and so on up to 1 minus Z9. Notice that because Z1, Z2 up to Z9 are the 10th roots of unity, the polynomial x10 minus 1 factors as x minus 1 into x minus Z1 into x minus Z2 and so on up to x minus Z9. Also, we know that x10 minus 1 factors as x minus 1 into x9 plus x8 plus x7 and so on up to x plus 1. So now if you compare the equations 1 and 2, what will we get? So we get that the polynomial x9 plus x8 and so on up to x plus 1 is equal to the polynomial whose linear factors are x minus z1, x minus z2 and so on up to x minus z9. Taking x equal to 1, we will get 10 is equal to 1 minus z1 into 1 minus z2 and so on up to 1 minus z9. So this will imply that the absolute value of the 1 minus z1 times 1 minus z2's absolute value and so on up to the absolute value of the complex number 1 minus z9 divided by 10 is equal to the absolute value of the complex number 1 minus z1 times 1 minus z2 and so on up to 1 minus z9 divided by 10 is equal to 10 by 10 which is equal to 1. So we see that the option B is also true. So let us mark this option also. Let us consider the options C and D together. For this, we will compare the coefficient of x8 in the equation star displayed in this slide. The coefficient of x8 on the left hand side is 1, whereas the coefficient of x8 on the right hand side is minus of z1 plus z2 and so on up to z9. And hence, comparing the coefficient of x8 in the equation star, we get 1 equals minus of z1 plus z2 and so on up to. Let us substitute the value of zk in this equation and simplify it further. So we will get that summation k goes from 1 to 9 cos 2k pi by 10 plus I sin 2k pi by 10 equals minus 1. The summation is over both for imaginary part and the real part. Separating the real and imaginary part of this equation, we will get that summation k goes from 1 to 9 cos 2k pi by 10 plus I summation k goes from 1 to 9 sin 2k pi by 10 is equal to minus 1. Now, comparing the real part and imaginary part in this equation, we will get that summation k goes from 1 to 9 cos 2k pi by 10 is equal to minus 1 and summation k goes from 1 to 9 sin 2k pi by 10 is equal to 0. So let us see which options among C and D are true. So option C, we have seen that summation of k goes from 1 to 9 cos 2k pi by 10 is equal to minus 1. So option C is not true. Whereas we have seen that summation k goes from 1 to 9 sin 2k pi by 10 is equal to 0. So this option is true. Let us mark this option. Hence, we have solved this problem completely. Before proceeding further, I would like to ask a question. What will happen if you replace 10 by an arbitrary positive integer? Which of the options among A, B, C and D are still true? I would like to give a remark before proceeding further. Suppose I take zk to be a complex number whose real part is cos 2k pi by n and whose imaginary part is sin 2k pi by n, where k is in the range 1, 2 and so on up to n minus 1. Then, as we have seen in the case n equal to 10, for every complex number zk, there is a complex number zj such that zk times zj is equal to 1. How will we prove this? So recall, as in the case of n equal to 10, zk is equal to e to the power I 2k pi by n. These are known as the nth roots of unity. That means zk to the power n is equal to 1 for all k is equal to 1, 2 and so on up to n minus 1. As in the case of n equal to 10, verify that zk times zj is equal to zk plus j for every integers k and j, where j may not be in the given range. So if you take j equal to n minus k, then zk times zj is equal to zk times z n minus k is equal to zn. What will be zn? So zn will be equal to e to the power I 2 pi, which is equal to 1. Also, since k is in the range 1, 2 and so on up to n minus 1, j equal to n minus k is also in the same range, that is 1, 2 and so on up to n minus 1. This proves that for every complex number zk, there is a complex number zj such that zk times zj is equal to 1. Let me give a remark too. The product of the absolute value of 1 minus z1, the absolute value of 1 minus z2 and so on up to the absolute value of 1 minus zn minus 1 divided by n is equal to 1. Let us prove this. The proof is similar to the case n equal to 10. So we have, because zk's are nth roots of unity, xn minus 1 is equal to x minus 1 into x minus z1 into x minus z2 and so on up to x minus zn minus 1. Also, xn minus 1 factors as x minus 1 into xn minus 1 plus xn minus 2 and so on up to x plus 1. By comparing the equations 1 and 2, we get that x minus z1 into x minus z2 and so on up to x minus zn minus 1 is equal to xn minus 1 plus xn minus 2 plus and so on up to x plus 1. Therefore, taking x equal to 1, we get 1 minus z1 into 1 minus z2 and so on up to 1 minus zn minus 1 is equal to n. Therefore, the absolute value of 1 minus z1 times the absolute value of 1 minus z2 and so on up to the absolute value of 1 minus zn minus 1 divided by n is equal to, recall that the absolute value distributes over the product. So, this is equal to the absolute value of 1 minus z1 times 1 minus z2 and so on up to 1 minus zn minus 1 whole divided by n. This is equal to n divided by n, which is equal to 1. So, this proves the remark 2. Let me give a remark 3 now. In the case of n equal to 10, we have seen what is summation of cos 2k pi by 10 and what is summation sin 2k pi by 10, where summation is in the range from k equal to 1 to 9. More generally, for any positive integer n, we have similar result. So, how will we prove this one? From equation 1, we see that the sum of the roots of the polynomial xn minus 1, which is equal to 1 plus z1 plus z2 plus and so on up to zn minus 1 is equal to 0. So from equation 1 we get 1 plus z1 plus z2 plus and so on up to zn minus 1 is equal to 0. This implies that z1 plus z2 plus and so on up to zn minus 1 is equal to minus 1. Let us substitute the value of z case and separate the real and imaginary part of the complex number on the left hand side. So we have summation k goes from 1 to n minus 1, zk is equal to minus 1. This implies that summation k goes from 1 to n minus 1 cos 2k pi by n plus I sin 2k pi by n is equal to minus 1. Now, separating the real and imaginary part of the complex number on the left hand side, we get that summation k goes from 1 to n minus 1 cos 2k pi by n plus I summation k goes from 1 to n minus 1 sin 2k pi by n is equal to minus 1. This in turn implies that summation k goes from 1 to n minus 1 cos 2k pi by n is equal to minus 1 and summation k goes from 1 to n minus 1 sin 2k pi by n is equal to 0. This proves the remark. In the last problem, we have seen several properties of the nth roots of unity. Let me discuss one more question on roots of unity. So let omega be a complex cubed root of unity. Then the question asks for the possible values of n so that 3 minus 3 omega plus 2 omega square to the power 4n plus 3 plus 2 plus 3 omega minus 3 omega square to the power 4n plus 3 plus minus 3 plus 2 omega plus 3 omega square to the power 4n plus 3 equals to 0. This is a descriptive question. Before solving this problem completely, let me remark that it is difficult to solve this problem directly. That means because omega is a cube root of unity, we know omega is equal to e to the power 2 pi I by 3. Also use the value that omega is equal to 4 pi I by 3. But it is difficult to solve this problem directly using this value of omega. The solution which we will be discussing here uses some properties of the cube roots of unity. Let us recall these properties. So first property which I want to recall is that since omega is a cube root of unity, omega cube is equal to 1, which implies that omega cube minus 1 equal to 0, which in turn implies that omega minus 1 into omega square plus omega plus 1 equal to 0. But since omega is distinct from 1, we get that omega square plus omega plus 1 equals to 0. We will be using these properties frequently. Second property which I want to recall is that again, since omega is a cube root of unity, omega cube is equal to 1, this implies that omega inverse
is equal to omega square. Also, since omega is a cube root of unity, omega to the power 3k is equal to 1 for every integer k. Why? Let us see a quick proof of this one. What is omega to the power 3k? Is same thing as omega cube to the power k by the loss of indices is same as 1 to the power k is equal to 1. I will use these properties to solve this problem. Let me remark that many problems on the cube roots of unity can be solved using these properties. Our problem deals with 4n plus 3 powers of 3 complex numbers. So let me name these complex numbers. So let E1 is equal to the complex number 3 minus 3 omega plus 2 omega square. E2 equal to be the complex number 2 plus 3 omega minus 3 omega square, and E3 be a complex number minus 3 plus 2 omega plus 3 omega square. A key point in solving this problem is that there is a relation between the complex numbers E1, E2 and E3. Can you guess what is this relation? So observe that E1 equals to, if I take omega common from E1, I get 3 times omega inverse minus 3 plus 2 omega. Since, as I remarked before, omega inverse is equal to omega square, this is equal to omega into 3 omega square minus 3 plus 2 omega, which is equal to omega times E3. Similarly, if I take omega square common from E2, what will I get? Omega square times 2 to the power omega to the power minus 2 plus 3 times omega to the power minus 1 minus 3, which is equal to omega square into, so recall that by previous remark, omega to the power minus 2 is equal to omega, whereas omega inverse is equal to omega square minus 3. So which is again equal to omega square times E3. This is an important observation. So let me highlight this, that E1 is equal to omega E3 and E2 is equal to omega square E3. The given equation is E1 to the power 4n plus 3 plus E2 to the power 4n plus 3 plus E3 to the power 4n plus 3 is equal to 0. By previous observation, this gives that since E1 is equal to omega times E3, omega E3 to the power 4n plus 3 plus, since E2 is equal to omega square E3, omega square E3 to the power 4n plus 3 plus E3 to the power 4n plus 3 is equal to 0. This in turn gives that omega to the power 4n plus 3 plus omega square to the power 4n plus 3 plus 1 times E3 to the power 4n plus 3 is equal to 0. Note that E3 is not equal to 0.
Why? Because E3 is equal to what? E3 is equal to minus 3 plus 2 omega plus 3 omega square, which is equal to what? Since we know omega square plus omega plus 1 equal to 0, writing omega square in terms of omega and 1, we get that omega square is equal to minus omega minus 1. This gives that E3 is equal to minus 6 minus omega, which is not equal to 0 because the imaginary part of omega is non-zero, whereas the imaginary part of 6 is 0. Therefore, we get that omega to the power 4n plus 3 plus omega square to the power 4n plus 3 plus 1 is equal to 0. This implies that omega to the power n plus 3 times n plus 1 plus omega square to the power n plus 3 times n plus 1 plus 1 equals to 0. Since omega to the power 3k is equal to 1 for every integer k, we get that omega to the power n plus omega square to the power n plus 1 is equal to 0. That is omega n plus omega to the power 2n plus 1 equals to 0. Recall that in the question we are asked to find the values of n so that the equation given in green here is true. We have seen that this implies that omega n plus omega to the power 2n plus 1 equals to 0. In fact, we can reverse the arrows in all these implications and see that the equation given in green here is true if and only if omega n plus omega to the power 2n plus 1 equals to 0. We divide all possible integers in 3 parts. The one which are multiples of 3, second one which are of the form 3k plus 1 for some integer k, and the third case is when integer is of the form 3k plus 2 for some integer k. Let us consider the case when n is a multiple of 3. So n is of the form 3k for some integer k. Then what will be omega to the power n plus omega to the power 2n plus 1. In this case, we get that omega to the power n is equal to omega to the power 3k plus omega square to the power 3k plus 1 is equal to, recall that omega to the power 3k is equal to 1 for every integer k. So this will be equal to 1 plus 1 plus 1, which is equal to 3, not equal to 0. So in the case of n is of the form 3k, we see that the equation in green here is not true. So now let us consider the case when n is of the form 3k plus 1 for some integer k. Then omega n plus omega to the power 2n plus 1 is equal to omega to the power 3k plus 1 plus omega to the power 2 times 3k plus 1 plus 1. Again, since omega to the power 3k is equal to 1 for every integer, we get that omega plus omega square plus 1, which is equal to 0 by the remark which I gave before. So let me recall that. So by remark 1, we know that omega square plus omega plus 1 equals to 0. So we see that if n is of the form 3k plus 1, then omega n plus omega 2n plus 1 equals to 0. Let us see what happens if n is of the form 3k plus 2 for some integer k. Then omega n plus omega 2n plus 1 is equal to omega to the power 3k plus 2 plus omega square to the power 3k plus 2 plus 1. Again, since omega to the power 3k is 1 for every integer k, this is equal to omega square plus omega 4 plus 1. But since omega to the power 4 is same as omega, we get that this is equal to omega square plus omega plus 1. Again, as we have seen in the remark before, that this is equal to 0. Thus, omega n plus omega 2n plus 1 equals to 0 if n is of the form 3k plus 2. So answer for the given question is, if 3 does not divide n, then the equation e1 to the power 4n plus 3 plus e2 to the power 4n plus 3 plus e3 to the power 4n plus 3 equals to 0. In fact, these are all the solutions of the given equation, since we have seen that if 3 divides n, then this equation is not true. Let us consider the next problem, which is on the absolute value of the complex number and the argument of the complex number. So question is the following. Let z1 and z2 be two distinct complex numbers, and let z be a complex number of the form 1 minus t times z1 plus t times z2 for some real number t which lies between 0 and 1. Then the question asks which of the options given below is true. Again, this is a multiple choice question, so it may be possible that more than one options are true. Option A is that the absolute value of the complex number z minus z1 plus the absolute value of the complex number z minus z2 is same as the absolute value of the complex number z1 minus z2. Option B is about the argument of the complex number, which I will recall shortly. So it says that the argument of the complex number z minus z1 is same as the argument of the complex number z minus z2. Option C is that the determinant of the 2 by 2 matrix, which is given here, is 0. Here z bar denotes the complex conjugate of the complex number z, which I will recall shortly. Option D is that the argument of the complex number z minus z1 is same as the argument of the complex number z2 minus z1. Let us discuss each options one by one and see which of them are true. Let us consider the option A first. Recall that for a complex number z is equal to x plus iy, the absolute value of the complex number is the positive square root of x square plus y square. We will solve this problem geometrically. For this, I will recall what is known as the Argand diagram. It is a diagram in which every complex number can be identified with a point in the Cartesian plane.
That means if z is a complex number x plus iy, then we can identify it with the point x comma y in the Cartesian plane. Then what does this modulus of z represent? This is nothing but the length of the line joining origin with the point z. So in other words, if you call this point as A, then modulus of z is equal to the length of AO. In our problem, we are given two complex numbers z1 and z2 and the point z which lies on the line joining z1 and z2. Notice that since z is of the form 1 minus t times z1 plus t times z2, if t equals to 0, then z is equal to z1, whereas if t is equal to 1, then z is equal to z2. Since the t lies in the interval 0 to 1, z is distinct from z1 and z2, and z lies on the line segment joining z1 and z2. Then what is the absolute value of z minus z1? This is nothing but by the law of parallelogram is equal to so let me complete this parallelogram first, is the following. So if you write this is our complex number z1, whereas this is our complex number z, then by the law of parallelogram of vector addition, we have that z1 plus, so let me call this segment as W. Then it says that z1 plus W is equal to z, so that W is equal to my complex number z minus z1. Therefore, the absolute value of the complex number z minus z1 is nothing but the length of the segment joining z and z1. Whereas the absolute value of the complex number z minus z2 is nothing but the length of the line segment joining z minus z2. Similarly, the absolute value of the complex number z1 minus z2 is nothing but the length of the segment joining z1 and z2. Hence, it is clear that the absolute value of the complex number z minus z1 plus the absolute value of the complex number z minus z2 is equal to the absolute value of the complex number z1 minus z2. So, the option A given to us is true. So, let us mark this option. Let us consider the option B now. So, recall that option B is about the argument of the complex number. Let me recall what is meant by the argument of the complex number. Just now we have seen that given any complex number z is equal to x plus iy can be identified with a point x comma y in the Cartesian plane. So
recall that we can write this complex number x plus iy using the polar coordinates of Cartesian plane as the follows. So we can write x in the form r cos theta and y in the form r sin theta. So this complex number has the form r times cos theta plus I sin theta for some non-negative real number r and some real number theta. This theta is the argument of the complex number z. So geometrically, if z is the complex number x comma y, then theta is nothing but the angle it makes with the positive real axis. Since cosine and sine are 2 pi periodic, the theta is not unique. To make it unique, we define what is known as the principal argument of the complex number. Let us denote by capital ARG of Z the principal argument of Z. What is this? This is nothing but the unique theta. So remember, it is unique theta such that z is of the form r cos theta plus I sin theta and theta is between 0 and 2 pi. Note that there is nothing special about the interval 0 to 2 pi. In fact, one can fix any interval of length 2 pi on the real line and define the principal argument of z as the unique theta which lies in that interval, and z has the form r times cos theta plus I sin theta. So again, we will solve this problem geometrically. Recall we have given two complex numbers z1 and z2, and z is a point which lies on the line segment joining z1 and z2. What is the argument of the complex number z minus z1? We have seen that this complex number can be identified as follows using the parallel law of vector addition. So this is the complex number z minus z1. Similarly, z2 minus z1 can be identified with this point. Hence, it is immediate that the angle that the segment joining origin and z minus z1 makes with the positive real axis is same as the angle that the line segment joining origin and the complex number z2 minus z1 makes with the positive real axis. So, therefore, the principal argument of the complex number z minus z1 is same as the principal argument of the complex number z2 minus z1. But note that the complex number z minus z2 is in the opposite direction of the complex number z2 minus z, and hence the angle that the complex number z minus z2 makes with the positive real axis is theta plus pi, where theta is the principal argument of the complex number z minus z1. So we see that the option B is not true, whereas the option D is true. Let us consider the option C now, which is on the determinant of the 2 by 2 matrix. Let us name this matrix. So let A be a matrix which is of order 2 by 2, whose first row is z minus z1 and its second entry is z bar minus z1 bar, and second row is z2 minus z1 and whose next entry is z2 bar minus z1 bar. Since the entries of the matrix involve the complex numbers z minus z1 and z2 minus z1, let us see how they are related. Since we know that the complex numbers z minus z1 and z2 minus z1 have the same principal argument, we can write z minus z1 is equal to lambda times z2 minus z1 for some real number lambda. Recall that for a complex number z is equal to x plus iy, the complex conjugate of z is the complex number z bar defined as x minus iy. It is not difficult to verify that if z1 and z2 are two complex numbers, then complex conjugate of z1 plus z2 is same as the complex conjugate of z1 plus the complex conjugate of z2. And similarly, the complex conjugate of z1 times z2 is same as the complex conjugate of z1 times the complex conjugate of z2. Now, since z minus z1 is equal to lambda times z2 minus z1, we have z minus z1 bar is equal to lambda times z2 minus z1 bar. This in turn implies that since the complex conjugate distributes over the sum, z bar minus z1 bar is equal to lambda bar times z2 minus z1 bar, but since lambda is real, this is equal to lambda times z2 bar minus z1 bar. As lambda is a real number and again the complex conjugate distributes over the sum. Therefore, determinant of the matrix A is equal to lambda times z2 minus z1 and its second entry is lambda times z2 bar minus z1 bar, and its second row is z2 minus z1 and its second entry is z2 bar minus z1 bar, which is clearly equal to 0. Thus, the option C given to us is true. So let us mark this option. This finishes the first lecture on complex numbers. In the next lecture, we will discuss some more problems on complex numbers. Thank you.